Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory undergraduate abstract algebra based on my book Algebra in Action, a course in groups, rings, and fields. And we are in the ring theory section. And the purpose of this lecture is to tell you what's an ideal. So let's get started by telling you what the plan for this lecture is. I'm going to tell you briefly, remind you what a ring is, what an ideal is, and what are ideals defined in this particular way. In fact, I have other videos on ring theory and go through the definitions and so on in more detail, but I will remind you what rings are and what ideals are and why are they defined here. I will also remind you what a ring homomorphism is and the relationship between the ideals and the kernels of ring homomorphisms and the relationship between ideals and quotient rings. In fact, ideals, ring homomorphisms, and quotient rings are different lenses for looking at the same thing. This will become a little bit clear here, but much more clear after we talk about homomorphism theorems in future videos. Okay, so what's a ring? So let's just think about some examples. A ring is a place where you have two operations. So the integers are prototypical ring. The integers you can add and you can multiply. But you can, and because you can add, you can also subtract, but you can't divide. Because you can 2 divided by 3 would be 2/3, and that's not an integer. But there are other objects like that. For example, polynomials with integer coefficients, what we denote by zx. That's also, polynomials are a place also, we can add polynomials, we can also subtract, we can multiply polynomials, but we can't divide polynomials with integer coefficients and get another polynomial. We get a rational function instead. But we don't have to have the coefficients be integers. We could have polynomials over the real numbers with coefficients being reals. That would also be an example of a ring. Integers mod n, we can add them, we can multiply modulo n, and that also forms a ring. Again, I have other videos that go through these examples in more detail. N by n matrices with real entries are also another ring. You can multiply matrices and you can add them. If they're n by n, you can add them. If they're n by n, you can multiply them. And they follow the properties of ring, which are what? So a ring is a set. It could be any set. The power of abstract algebra is that we apply the same sort of principles to a wide range of situations. So we start with just a set whose elements we actually don't know. They could be integers, they could be polynomials, they could be matrices, they could be integers mod n, it could be a variety of different things. And these are just some examples. There could be a lot of other things other than these. So a ring is a set of elements, and it has 2 operations. One operation is addition, the other one operation is multiplication. With operation, we ask a lot. We want the set together with an operation to be an abelian group. So what does that mean? That means that when you add it, you have closure. When you add 2 things, you get something in the ring. You have associativity. A plus B plus C is the same as A plus B plus C. You have an identity. You have something we call a zero, that when you add to other things, nothing happens. And for every element, you have an additive inverse. You have something that when you add to it, you get 0. And then we want it to be abelian. That's another word for commutative. We want that addition to be commutative. And we, in a previous video, in a different video, we have talked about why that addition needs to be commutative. With multiplication, we don't require that much. We just require closure and associativity. So if you take 2 elements and multiply them, it has to stay within the ring, and AB times C should be A times BC. Now we call these operations addition and multiplication, but they don't have to be the actual addition and multiplication of numbers, because the objects we work with are not necessarily numbers. So for every situation, we also have to know not only what the elements are for when we want to apply ring theory to a specific situation, but we also have to know what the operations are. What's the plus and what the addition? We also have to have distributive laws. A times B plus C should be AB plus AC. But what you sort of basically need to know is that you can add, you can subtract and multiply in a ring, but not necessarily divide. Now, some notation, the additive identity of R, the elements that when you add to other things, nothing happens, we denote by 0. If the R has a multiplicative identity, something that when you multiply by things, then it doesn't change, then we denote that by 1. Now, some authors insist that every ring should have an identity, and they have reasons for that. And those people, they call a ring without an identity a ring. They drop the I in the ring. But for us, that's not the thing. A ring or a subring may or may not have an identity. And that makes it a little bit more, there's more things that we can say, but more importantly, when I talk about a ideal, it can be a subring, and I prefer that. But this is a preference. Many people, many places do as I do, but some places insist that a ring should have an identity, and you should be careful with that in terms of when theorems are stated. Talking about ideals, and I want to start by giving you some examples. So Z, the set of integers, is a ring. You can add, you can multiply, and it has all the properties that we want. And a subring of that is multiples of 5, 5Z. 5Z would be things like 5, 15, minus 10, any multiple of 5 among the integers. Now, 5Z is a subring, so it's closed under addition, subtraction, and multiplication. It's a ring in its own right. By the way, it's a ring that does not have a multiplicative identity. It doesn't have a 1 in it. It doesn't have anything that when you multiply by other things doesn't change. So for multiplication, there's actually more true than just taking two elements of 5Z and multiplying them and getting something in 5Z. What's true is that if you actually take any multiple of 5 and multiply it by any integer, it doesn't have to be a multiple of 5. It doesn't have to be in the subring. You get a multiple of 5. This property, this sort of strong property, is what makes ideals ideals. Let's look at another example. Look at polynomials with integer coefficients. That's also a ring. You can add two such polynomials or multiply them and get one other element like that. And look at the set of polynomials. Then when you plug 2 in, you get 0. So these are polynomials that have 2 as a root. So things like x minus 2, or x minus 2 squared, or x minus 2 times x plus 3. So those kinds of polynomials. Any polynomial with integer coefficients that when you plug in 2, you get 0. So that's also a subring. If you add two such polynomials, if you have two polynomials that when you plug in 2, you get 0 and add them, you still get a polynomial that when you plug in 2, you get 0. Same thing if you multiply them. But again, with multiplication, more is true. If you take any polynomial that when you plug in 2, you get 0, and then multiply it by any polynomial, not necessarily one that is in S, is in this subring, but any polynomial, you will still get something that when you plug in 2, you get 0. So again, 5Z is an example of an ideal and of the integers, and S is an example of an ideal of the polynomials over the integers. An ideal is really what makes it is a subring, so closed under addition and subtraction and multiplication. But then the multiplication part, there's more to it. It's closed under multiplication with a vengeance. Not only you get to multiply two elements in the ideal and get something in the ideal, you get to multiply something in the ideal by anything and still stay within the ideal. And that notion is what ideal wants to capture, that thing that we see happens. Multiple 5s have that property. Polynomials, when you plug in 2, you get 0, have that property. Those are very different kinds of situations, but this property is what we want to capture with the notion of ideal. So here's the definition then. So we have a ring. When we say a ring, I'm identifying the addition and multiplication that I put. That's why I put R with a parentheses and plus and times. If you are talking about a specific example, when those things are understood, what the addition and multiplication are, then you don't have to put them in. So we have a subset I. This I is going to be an ideal if it satisfies certain conditions. And we call it an ideal or a two-sided ideal, because in the cases where the multiplication is not commutative, we can have left and right ideal, and I'll mention that in a second. So first of all, it has to be a subring, so that means that it has to be closed under addition, multiplication, and subtraction, and it has to be non-empty, and more than that, it has to have this extra property that not only closed under multiplication by elements in I, but closed under multiplication when you take an element in I and multiply it by anything in the ring, it should stay in I. So when you multiply elements of the ring by elements of the ideal, they get absorbed in the ideal. So again, an ideal, the closure under multiplication is stronger than one for a subring. So now, if instead of having if you only could multiply ring elements on one side and assure yourself that you get something in the ideal, then you would call that a left ideal. Left ideal, you're multiplying on the left by ring elements. And that would be an example of a one-sided ideal as opposed to a two-sided ideal. And vice versa, if you multiplied on the right and you preserved being in I, then that would be called a right ideal. And a two-sided ideal is just an ideal that's both a left and a right ideal. So this matters in rings where the multiplication is not commutative, like, for example, matrices. But it doesn't really matter in commutative rings, which most of the lectures in this actually introductory section are going to be about commutative rings. So ideals, what's their importance? Well, if you've done group theory, ideals are to rings what normal subgroups are to groups. Normal subgroups played an outsized role in group theory and much more than subgroups. I mean, subgroups are important in group theory too, but normal subgroups were even much more important. And the same thing goes for ideals. And in fact, in ring theory, we hardly ever talk about subrings. We try to translate everything into the language of ideals. In another video, I talked about ring homomorphisms, and I discussed kernels of ring homomorphisms, those elements that go to zero, and explained that those are ideals. And in fact, in that way, in fact, ideals are defined as the subrings that can be the kernels of ring homomorphisms. So that's one thing that ideals do, is that they end up being kernels of ring homomorphisms. Again, I have another video for that purpose. Each ideal also produces a nice partition of the ring, and I will describe that in a second. And with ideals, we can define quotient rings. And I will mention that here, although other videos will go into more detail. In fact, as I had said before, ideals, ring homomorphisms, and quotient rings are different lenses for observing the same phenomena. And in ring theory, again, as I said before, we want to translate almost any concept we can think of to one about ideals, about these substructures that have nice properties. Okay, so ring homomorphisms. What's the relationship with ideals and ring homomorphisms? So if you have two rings, R and S, then you might have a map from R to S. So they say phi sends elements of R to S. So it's a map. Any element of R you can plug into phi and you get something in S. And when you plug in some element in phi, you get one element in S. You don't get two elements in S. But the map may or may not be one-to-one and onto. Two different elements might go to the same place. And it might be that not all of S is hit by elements of R. Now, if you take an element A in R, it goes somewhere, phi of A. And if you take another element B, it goes somewhere to phi of B. But if this map is going to tell us something about the ring structure, it can't then just send everything everywhere it wants. If it sends A to phi of A and B to phi of B, where should it send A plus B? Well, if it wants to tell us something about what rings do, it should A plus B is the sum of A and B, so it should go to the sum of phi of A and phi of B. So A plus B should go to phi of A plus phi of B. This is sort of if there's justice in the world. So phi of A plus B should be phi of A plus phi of B. It may or may not be, but if it is, and if the same thing is true, so if phi of A plus B is phi of A plus phi of B, no matter what A and B are, and also if, same thing, phi of AB is phi of A times phi of B for all A and B, then we like this map a lot, and we call it a ring homomorphism. Again, I have other videos on ring homomorphisms, but this is basically what it is. This is the definition of a ring homomorphism. If you have a ring homomorphism, then the kernel of the map is all those elements that go to zero. Those are the elements in the domain that are mapped to the zero of the codomain. The codomain is a ring, and so it has a zero. So some elements go there. In fact, one can prove, and in the ring theory, in the homomorphism video I have, that zero, for example, zero of R will always go to zero of S if you have a ring homomorphism. All other things that go to zero together with zero are called the kernel. And the kernel is an ideal of R. And that's not hard to see. Again, in the other video, I've explained this in more detail. If you have something in the kernel, that means that if phi of A is zero, and if you take some element of the ring R and multiply and find RA, what's phi of RA? Well, phi of RA is going to be phi of R times phi of A, because this is a ring homomorphism. But phi of A is zero, and phi of R times zero will be zero. So phi of RA will be zero, and the same with phi of AR. That will be zero as well. So if you have something in the kernel, when you multiply it by anything in the ring, you get something in the kernel as well, and that makes the kernel an ideal. So that's just a proof of that. What's also so kernels of ring homomorphisms are ideals. That's what I just argued. But the other interesting thing that I'm not in the position to tell you quite yet why, but I can in a future video, is ideals are kernels of homomorphism. So in the sense that if an ideal walks through the door, not a homomorph, if a ring homomorphism walks through the door, you know the kernel is an ideal. But what if an ideal walks through the door? And the answer is that it is also a kernel of homomorphism in the sense that there will be a homomorphism out there that ideal will be its kernel. So kernels and ideals are sort of two different names for the same thing. Now, I want to briefly tell you the connection with quotient rings. Again, other videos will go into more detail about this. So if you have a ring homomorphism, the kernel is so here we have a ring homomorphism from R to S. It's not going to go to all of S. It's going to be really a map to the image of phi, whatever that is. What are the elements that are hit? The kernel is those elements that are mapped to 0. So the kernel of phi are all the maps that are mapped to the 0 of S. But that's not all the elements. So you might pick another element A, and that might go somewhere else to phi of A. But if A goes to phi of A, then so does A plus kernel of phi. So that means that if you take A and add to it an element of kernel, that will also go to phi of A, because phi of A plus something in the kernel is phi of A plus phi of that something in the kernel, but phi of that something in the kernel is 0, so you just get phi of A. So not only A goes to phi of A, but A plus kernel of phi goes to phi of A. Now, if you remember, or if you've done your group theory, you know that this is called the coset of the kernel of phi. But this is what it is. You take the kernel of phi, this ideal in this case, which happens to be also a normal subgroup of the ring when you look at a division, and their addition is an abelian group. So this is a normal subgroup. So A plus kernel of phi is a collection of things. What is it? A plus everything in the kernel. All of those elements go to phi of A. And same thing with other things. So if you take something that's not in the kernel or not in A plus kernel of phi, say B, that goes to phi of B, but B plus kernel of phi will also go to there, and this will continue. And on the left-hand side here, we actually get a partition of R. No two of these things are the same. They're elements that go to different places, and one can show that. And you get everything, because if there's something that you didn't get, well, see where that goes, because the R is the domain, and that guy is sent somewhere, and then its cosets, it plus the kernel, will be all the elements that go over there. And so this is giving us a partition of R. Now, image of phi, image of a ring, is going to be a ring. So these elements that we get here are not all the elements of S, they're the image, but it's a ring. And so we can add them, we can multiply them, and they follow the rules that we like. Now, the cosets of the kernel also form a ring. So if you look at these boxes over here, they're not just one element, but they're sets of elements. But those sets, we can think of them as forming a ring. And in fact, they form exactly the same ring as this other side, because the addition and multiplication of those that we're going to define is going to just mimic what happens over there at the image. So now addition is actually not ever going to be a problem, because of the fact that A plus kernel of phi plus B plus kernel of phi, it's A plus B plus kernel of phi. Again, when we talk about quotient rings, maybe I'll go through this in more detail, but that follows from group theory, because R with addition is a group, and kernel is a normal subgroup, and so addition will not be a problem. But more is true here is that we can make the cosets into a ring by defining a multiplication, and we can define that by saying that A plus kernel of phi times B plus kernel of phi is AB plus kernel of phi. So A plus kernel of phi, what is that? Those are all the elements of the ring that are of the form A plus something in the kernel. B plus kernel of phi, all the things of the form B plus something in the kernel. AB plus kernel of phi is things in the kernel plus AB. But why are those the same? That doesn't necessarily have to be the same. The reason that that's the same, and the reason we have this multiplication on the left that says that if we can multiply these two and we get the AB one, so the same as here, phi of A, phi of B would give us phi AB, we can multiply the ones on the left as well. The reason we can do that is because that when you multiply that out, if you take A plus something in the kernel times B plus something in the kernel, what do you get? Well, you get AB, you have got to FOIL it. You get AB, but then you get A times something in the kernel, and then you get plus kernel plus something in B, and then you get two elements of the kernel multiplied. The two elements of the kernel multiplied will give you something in the kernel, but it's important that when you multiply A by that element of the kernel and some element of the kernel by B, you also get something in the kernel, so that they all add up together to one thing in the kernel. So this property that we define for ideals, the fact that something in the ring times the kernel should be in the kernel, is exactly what we need to be able to define this ring of cosets, so that we can make these boxes, these sets, as elements of a new ring. And that's called the quotient ring, and it's the set of the cosets. And again, if you had seen group theory, you have seen quotient groups, and this is actually the same elements with the same addition as you would have done in group theory, but now we've added a ring theory element, multiplication to it. And the point of this slide, which may have been a little bit vague, is that we could not have done that unless the kernel had the property that ideals have, which is that when you take something in the kernel and multiply it by something in the ring, you stay within the ideal. Okay, so let's give a specific example. So again, the ring is going to be the ring of polynomials with integer coefficients, and I'm going to take S to be that ideal that we introduced at the beginning of these lecture, which is polynomials that when you plug in 2, you get 0. Okay, so that's an ideal again, and I'm going to define now a map, a homomorphism. So again, whenever you have an ideal, you can come up with a homomorphism that ideal is the kernel of. We will do that in general in a later video, but in this case, I'm going to define that very easily. It's going to be the map that sends any polynomial to what you get when you plug in 2. You just plug in 2 in it. That's a ring homomorphism, and S is its kernel. It's a ring homomorphism because if you plug in 2 in this polynomial and that polynomial and then add them, it doesn't matter if you first add them, then plug in 2, or plug in 2 and add them, and same with multiplication. That makes it a ring homomorphism. And the ones that when you plug in 2, you get 0, well, those are the kernel. Okay, so the picture that we have is that we have a map from the polynomials to integers. When you plug in 2 in, you get an integer. And these polynomials that have 2 as a root, are the ones that go to the integer 0. And then I can add 1 to those polynomials. Like, for example, x minus 2 goes to 0, because when you plug in 2, you get 0. I can add 1 to it, I get x minus 1. And when you plug in 2 in that, you will get 1. So that map phi sends it to the integer 1. If you added minus 1, it would go to the integer minus 1. If you add 2 to the elements of the kernel, any one of those polynomials that have 2 as a root, you get 2. Not a very profound idea, and this continues. So on the left, I have all polynomials, because all polynomials, when you plug in 2, you get some integer, and on the right, I have all the integers. And the point is that I can treat the left-hand side, the boxes in the left-hand side, as a ring, because they behave just like the ring on the right-hand side. And for that reason, we say that if you take the ring of polynomials and mod out by find the quotient ring, mod out by the ideal S, you will get a ring isomorphic to the integers. Again, when we do homomorphism theorems and quotient rings, we will talk about this in more detail. Okay, so now let me give you an example to see how could this fail. So let's take R to be the ring of real numbers. You can add and multiply and subtract real numbers very well. In fact, real numbers, you can do more. You can divide by non-zero numbers. It's actually a field, but it's a ring nevertheless. And the integers is a subring of that. The integers is also a ring, and it's sitting inside the reals, so it's a subring. But it's not an ideal, because if you take an integer, it's true that it's closed under addition, multiplication, and subtraction, but it's not, doesn't have that extra oomph if you take an integer and multiply it by a real number, you don't get an integer necessarily. So because of that, I cannot actually give you a homomorphism, ring homomorphism with this guy as an ideal, because any homomorphism that I give you, the kernel will be an ideal, and so there's no way to give you a ring homomorphism that has that goes from R to something and Z its kernel. Okay, so but what if we try to do the box thing and partition the real numbers in the same way? So we could say, well, okay, I've got the integers. It takes something that's not in the integers, maybe square root of 2, add it to the integers. Well, you get a whole bunch of real numbers that way. Maybe add pi to them, you get another set of them, and just continue that. You're not going to be able to list them like that because it's not a countable set, but you can imagine that you have boxes like this, and all real numbers are going to be in one of these boxes. So this does give us a partition of the real numbers. However, the problem is that we cannot define a well-defined multiplication. We can define an addition. So for example, square root of 2 plus z, that box, everything that's of the form an integer plus square root of 2, if you add that to anything that's of the form pi plus an integer, you do get something that's of the form square root of 2 plus pi plus an integer. So that part works. Addition works fine because the integers is a subgroup of the real numbers, a normal subgroup of the real numbers, when we're only focusing on addition and thinking of that as an abelian group. But multiplication does not work because the square root of 2 plus the integers, if you take an integer plus square root of 2 and then multiply that by an integer plus pi, you will not get an integer plus square root of 2 pi. You also get pi times something and square root of 2 times something, and it will not be of this form. So we cannot define this multiplication. We cannot define a quotient ring. Okay. So this was the end of this video. So again, I defined for you what an ideal was, and I told you some of the relations between ring homomorphisms and ideals, between quotient rings and ideals. For all of those things, I have other videos. The videos on that I are relevant at this point, there's a lot more videos than these, is that if you're new on to rings, there's a video on why rings and it gives you motivations through Diophantine equations, why we study rings. There's one that gives you basic definitions for rings, integral domains, and fields. There's one just gives you lots of examples. We have one that we focus on this question of identity. As I said, I don't assume that rings have identity. And another one on ring homomorphisms and their kernels, which actually I do define ideals. This one told you about ideals. The next one will tell you about principal ideal rings and more generally about generating ideals, especially in commutative rings with identity. And another video on Zorn's lemma and maximal ideals. And again, other ones on quotient rings and homomorphisms and so forth. If you want to be subject to videos like this on your feed, please subscribe. And if you like the video, like it. If you didn't like it, don't like it. See you next time.